Right. This video is going to be the second in a series of two. The first video talked about how to solve exponential equations. This video talks more about how to solve logarithmic equations. So an equation where you already have a logarithm, what do we do about that? Now, there's three really good ways depending on what kind of an equation you're looking at. For some of the really basic ones, just a simple inverse or conversion is really simple. One-to-one property is also very helpful. We'll show you an example of that in a minute. And condensing can also be very helpful for you, depending on if you have a fairly complex problem, that maybe that can come in handy. So the first one, first of all, let's talk about this log of x equals 4. Now, if we want to solve for x, one option is just to say, well, hey, if this is log base 10, right, we can just do that quick little swirl we've talked about in the past and know that 10 to the 4th power should be equal to x, which means we've just solved for x, right? 10 to the 4th power equals x. So on the right, you'll notice I've got 10 to the 4th there. Now another option, and what I actually used there in my options, was actually what we call exponentiating. It's using the inverse. Again, if log base 10 is present, why not do exponential base 10? So I took 10 to the power of, just like we did on the right, 10 to the 4th. I also did that on the left. I did 10 to the power of what I had there. So again, this side just became 10 to the log of x. On the right, we got 10 to the 4th. 10 to the log base 10 is just going to simply cancel away. And we'll end up with just x equal to 10 to the 4th. And 10 to the 4th is 10,000. I guarantee you, type it in your calculator, the common log of 10,000 should come out to 4. It's 10 to the 4th power. So again, exponentiating is a great way to go. If this would have been a log base 5, I would have done 5 to the power of. If it was a log base 7, I would have done 7 to the power of. Right? There's lots of ways to do that, taking advantage of whatever base you were given. Now, the one-to-one property, on the other hand, really comes in handy when you're dealing with multiple logarithms. Okay? And notice I'm equal to 0 over here. So the very first thing I'm actually going to do is take this really big logarithm, log base 2, of 3x plus 1. I'm going to add that to the other side. I'm going to go ahead and just add that whole term over here, and 0 plus that's just going to be log base 2 of 3x plus 1. Well, now if I have log base 2 of x and log base 2 of 3x plus 1, well, those two logarithms are equal to each other, so what's inside needs to be equal. That's that one-to-one property. Now, if you want the exponentiating behind it, like we did on the last screen, remember, if it's log base 2, I could say 2 to the power of, and 2 to the power of on this side. And again, log base 2 is going to cancel with the 2 to the power, 2 to the power of log base 2 on both sides, and basically we'll get that next statement, right? I had an x left over on the left, I had 3x plus 1 on the right. Subtracting that 3x and then dividing by -2, I simply get a -1/2. Now, I do have a slight problem with that though. -1/2, again, being a negative number, when I go to plug that back in, log base 2 of a negative number wouldn't be a real answer. So I can't have a negative solution. It's not going to work right here. So therefore, this one doesn't work. Again, you don't necessarily have to cross it out, but I wouldn't box it up like I did there. What I would want to say is that it's extraneous, and since it was my only solution, I would say that this problem actually has no solution, which you could easily check. Probably graphically might be the easiest way. If you actually graph this equation at the left, if you graph that left side equal to y, and then take a look and see if you get any x-intercepts. My guess is this. Those logarithms, right, are never actually going to cross the x-axis. You're never going to get any x-intercepts. So we would never be equal to 0. So again, keep that in mind with whatever kind of answers you get. You've got to make sure that they're not extraneous when you start. So I would actually want to go back here and make sure I would put that 10,000 in there. Again, log of 10,000 is 4. I would double check that, but I'm pretty sure that one does work. What if, again, you have those multiple logarithms, but you can't just get rid of one on the other side. You can't just move it over and kind of solve it that way. Well, condensing is another great idea. What if you have a log plus a log? Well, I'd love to put those as one logarithm multiplied. Now, I got to be careful first. I've got this 2 in front. So first, let's put that 2 up as an exponent. Now I can condense my logarithms into one logarithm multiplied. Then I can do a little exponentiating, right? Again, if I've got a log base 10, we'll do 10 to a power, 10 to a power on both sides, right? 10 to the fifth on the right. The log and the base 10 cancel there, so we get 6x squared on the left. We're going to divide by 6 next. Again, that's just a number waiting to be found, so no reason we can't find it. However, I'm going to go ahead and take the square root next. Don't forget to say plus or minus. And then again, there's my final answer. But now I got to remember again, when I plug those back in, on the right here, this log of x, I can't plug a negative number in there. Positive 129.099 should work. Approximately, it'll get you close to 5, or as close as a three-digit decimal can. Right? We're going to give our most accurate to 3 decimal places number we can. But again, the negative won't really work. So I should go ahead and say, right, that negative, I better write those separately, negative 129.099 would be extraneous, and 129.099 is actually my only good solution. Right? Make sure you check those answers when you get done. Logarithms have a limited domain. Right? They have that vertical asymptote. They only exist on half the graph. They have a limited domain. So you've got to be careful what you plug back into those numbers. Right? All right. Let's move to one last problem. Again, in a real world problem. Again, these are a little bit construed, but here's one example of where you might use a logarithm. It's just a research study had been done. P equaled 85 minus 12.5, the natural log of D, was a model to figure out the proficiency P percent after D days of not practicing something. So if I don't practice for how many days, I'll lose a certain number or a certain percentage of what I remember about that subject, right? That's why your math teacher tells you, keep doing your math, right? Take math every year. If you stop using it, you're going to forget it. Well, if I don't practice, what's the probability I score 50% on logs, right? How many days from now? Well, how long will it take before I basically lose half my information, right? If I haven't been using it. Or there's a good chance anyway, those skills will fade. Well, let's take our equation. We'll plug 50 in for P. Subtract 85 from both sides. And divide, right? Divide by that negative 12.5. To get rid of a natural log, we're going to do e to the power of. So e to the power of this fraction here, right? That's all up in the exponent. That's not e times, by the way. I know that e's not very large, so I'm going to enlarge it here a little bit. E to the power of that fraction, because e to the power of the natural log would have canceled away, right? We would have exponentiated. Put a nice big E over here. Exponentiate, right? And cancel away e to the natural log, which leaves just d, right? No longer trapped inside that logarithm. And now all I have to do is type my answer in. And it turns out it's about 16.445 days, or in the real world, we'd probably round that off to the nearest day, about 17 days or so. And you'll forget half your information. So therefore, keep practicing. If you have any questions, make sure you talk to your teacher. And of course, have a great day.